Well, welcome to Humpky's study once again. Office hours have been pretty lively this week, um, but I think we're getting things straightened out with regard to chapter 14, and I think I'm not going to do the last section of chapter 14, at least not yet. We're going to move on to integration. Lagrange multipliers is pretty interesting, though, so if we have some time, we'll go back and do it. I'll give you two little sheets to work on before Friday. The first one is kind of a review of what we've done in chapter 14, what you need to know, and the kind of problems that you can expect from the prof. So there's in the beginning of it, if you might want to open that up while I talk here. But in the beginning, there is something called specific context. This is the stuff that you would be given in any problem. So I'll give you a function. I give you a frame to look at it in. This is like the plate of the last test. And then I'll give you a bunch of curves or regions to deal with. And finally, a description, like I've done before, where the function might be a temperature function, something like that. Then in the next section, these are problems of various types that I would ask you to solve. Some are geometric, some are graphical, some are purely computational, and then some problems where you kind of put it together. So there's a whole series of questions. Many of them ask the exact same thing in kind of different ways. So go over those if you get a chance between now and Friday. And if there are questions as to how to deal with one of these problems, let me know. And you can use the functions that I gave you and the frame and the various regions to actually work these problems. So I suggest that you do that. I also wanted to talk a little bit about integration. And I'll do a little Calc 1 here to begin, and then we'll talk about how it works for Calc 2. And I'm going to go to the board, so I want to make sure that you can see this. So in calculus, when I give you, or when you're given an integral, say the integral of 0 to 1 of x squared dx, I'm going to take a look at where this notation comes from. What does this mean? Well, we're talking about the graph, y equals x squared, f of x equals x squared. And we're talking about a specific interval of x's, in this case, 0 to 1. But then we're talking about a process here. At a given x between 0 and 1, the distance between that x, vertical distance between that x and the graph, that is the x squared. That is a length. So I want you to think about that as a stub length. And x can be anywhere between 0 and 1. This kind of puts barriers on the problem. So we're only looking at this between 0 and 1. And this integral is asking you to add up these lengths in the x direction, beginning at 0 and ending at 1. So what's going on there is something like this. There's a start button. When the button starts, when I press that button to start, x will begin at 0, and x will slowly proceed toward 1. And as it does, this blue chalk line will move across the frame and leave a little chalk dust. Chalk dust is everywhere, by the way. Leave a little chalk dust as it moves. So, you ready? Let's take a look. I press the start button, and now the x starts here, and it's moving across. It's moving across slowly. Let's just do a stop for a minute. So it stopped at this position, and what has happened is it leaves this little trail of blue chalk, and it has filled up that region. When I start it again, it continues across, but then it automatically will end at 1, and it stops. So that is the procedure of integral. This symbol stands for summation, where you add up discretely 1 plus 2 plus 3. So n stands for a whole number, integer. Over here, this s that I've made a mess of, this s involved with integral stands for summation in German. And this is considered a continuous sum, continuously adding up these line segments in a parallel fashion, like stacks of disks of various sizes, beginning at 0 and ending at 1. The fundamental theorem of calculus says that, so fundamentally this measures an area. This measures area. That's the idea. This fills up area, and this integral is to measure area. The fundamental theorem of calculus says to do this, you can take an antiderivative, any antiderivative, evaluate between the endpoints, and get the answer. This is sort of marvelous that that's actually true, that this measure of the geometry, in this case, the area, can be obtained in this way very numerically from the function that you're given. Now, in higher dimensions, let's do this in 2 dimensions. In 2 dimensions, I'll draw the x and y axes here. The function axis, or the z-axis, will be here. And, well, maybe we'll call this x1 and x2, and this the y-axis. And maybe x1 will go between 0 and 1, and x2 will go between 0 and 1 as well. So our domain will be this little square, which I'll call S. And now if we want to integrate over this square S of some function, now if I graph a function over S, it will maybe look like some kind of sheet. So here is a surface, a function of 2 variables. And I'm going to add this up over the square. So this is not directional at this point. This is just adding it up over the square. What does it mean? It means that at any point in the square, we look at the height under that graph. And then the start button, when I press it, this point will move randomly and very rapidly all through this square. And when it finishes, it will fill up the entire volume under the surface. And that's what this integral means. This integral means that you sum up these lengths over that entire square. It's not exactly a computational process at this point, but you can think of this in the following way. We'll take a fixed y value, or in this case, I guess I used x1, x2. We'll take a fixed x2 value, say here. And the first thing we'll do is we will let that individual stub move from 0 to 1, but just along this fixed x2 line. And that will fill up a certain area, and that area will depend on what x2 is. After we're done with that, so we need a little more space here where I write a dx2. After we're done with that, then we'll let x2 vary between 0 and 1 and let this sheet fill up from the left-hand edge to the right-hand edge, filling up the entire volume. Now you might say, well, that's no different, but in a way it's very different than this first idea. This is called an iterated integral, by the way. This is called a double integral because it's over a two-dimensional region. So let me see if I can do that with a particular example. Let's suppose that f of x and y is x squared y plus 1. And now we want the double integral over 0, 1 cross 0, 1, the square. This is a double integral of x squared y plus 1. And I want to write that as an iterated integral. X will go from 0 to 1. We're still integrating the same function. We'll do the inside one first. Now, in this case, y is a fixed number. This is just a function of one variable with a fixed but unknown y. So the outside integral will remain the same. The inside integral, I'll use the fundamental theorem on. I'm integrating with respect to x. X cubed over 3 times y plus y, evaluated between 0 and 1. So this is nothing more than a one-dimensional integral for a fixed value of x, for a fixed value of y. It should be an x. I'm integrating with respect to x. So for a fixed value of y, y is a constant. This is the integral, and these are x values. So I sub in those x values, leaving the outer integral the same. If you sub in 1 for x, you get y over 3 plus 1. And if you sub in 0 for x, you get 0. And now we're left with a second integral, and this second integral is just a function of y. We can integrate it. We get y squared over 6 plus y, needed to be evaluated between 0 and 1. 1/6 plus 1, 7/6. And this double integral measures the volume under this curve. So the volume under that curve is 7/6. How do you do this double integral? We're going to try to do it as an iterated integral, first integrating with respect to one variable and then the other. So what is the hang-up then? What could be possibly complicated? This base is an oriented rectangle, which makes these limits very easy to find. If this base is more complicated, say a disk or a triangle, then such an integral becomes more complicated, but only because it's difficult to tell exactly what these limits of integration are. So a good deal of our work in here will be not involved with the anti-differentiation process, but involved with finding out how to describe regions in a suitable way that we can integrate over them. I'll give you a few problems from chapter 15, section 1 on this, but see you Friday. Looking forward. Take a look at that other homework too, and we'll talk about it on Friday. See you soon.